Iterative list processing, or the interface iterator. So today we're looking at the linked list again, and we're going to consider two situations. We're going to be writing some code when we are the user of the class linked list, and we're going to be writing some code as the implementer of the class linked list. So those statements will be written inside the implementation. Okay, so let's go here and look at this. So this is a lecture that I really like. I like it because it's a good occasion for us to reinforce many ideas. So for instance, this will reinforce the concept of encapsulation, object-oriented programming, the state of an object. That will be a very important concept, and the interface. It's also a good occasion to talk very intuitively about computational complexity, which will be introduced in your data structure course, CSI 2110 next year. So we're going to be talking about those ideas in a very intuitive way. So what is it that we want to do? Let me show you. So I have the interface list, and the interface list here is telling me that a list has some method size, some methods for adding elements, removing element, and a method get that returns the value stored at the position designated by index. I see that the indentation is not as it should, so here we go. So there's an implementation of the interface list, and when I'm programming, I decided to reuse our last implementation from the last lecture. So this is the one where I have a class node, static nested class node, and as you can see, the nodes are doubly linked. This is also the implementation that is circular, and it's using a dummy node. So you see here head, I only have one variable of type node for an object of the class linked list, and so this variable head will be pointing at the dummy node always. In a constructor, when a new list is created, this is where the dummy node is created, it will never store any information. It's not designed to store information. Its only purpose is to make all the operations simpler by removing special cases. And here is the place where I make the list doubly circular. So head.next is pointing at head itself, and head.previous is pointing at the dummy node itself. And here is an example where I'm in some class called test. I'm declaring a variable called colors to be a reference to a linked list object, creating the linked list, and I'm adding some strings. Bleu, blanc, rouge, jaune, vert, orange. So I now have 1, 2, 3, 4, 5, 6 elements inside this list. Here, I'm writing a method to traverse the list, to visit all the elements and print their value. I'm writing this inside the class test. Clearly, I'm not inside the implementation of the linked list. So, in order to do my work, I can only access the methods of the interface list, in particular in the method traverse, because that's the type of the parameter. So here we go. For some int I equals 0, I is smaller than the size of the list. I cannot access any instance variable, so I need to call the method size I++. I'm going to print So system out print line, and the only method that allows me to read or to obtain the content of an element at a certain position, it's the method get. So I'm using this. Save. Let's compile the test. Let's run. Okay, so I simply wanted to print the content of the list. I did that when I was outside of the implementation. Let's do the same thing inside the implementation of the list. I already have the code here. A method traverse. I'm using a variable of type node. I'm calling it current. Because I'm in the implementation where there's a dummy node, I will make current point at the first real element. I'm going to say, while current is different than head, go inside the loop, print current.value, move forward. Imagine the case where the list is empty. There's only the dummy node. When I say current equals head.next, head.next is pointing at the dummy node itself. When I test this, current is pointing at the dummy node, so therefore current different than head is false, so it does nothing. If there's only one element, current equals head.next, current will now be pointing at that element. Here, current is therefore different than head. We print current.value. We say current equals current.next. We're moving forward in the list. And now, because there was only one element, it was the last one of the list, current.next was pointing at the dummy node. So therefore, when I test is current different than head, it says false, and we exit. So you see the picture. This will work all the time. If the list is empty, if it has 1, 2, 3, 4 elements, it will print them all. Okay, let's compile our linked list.java. That compiles very well. Let's go here. So here, callers has a method called traverse, and we're calling it. Okay, so we're calling the method traverse of the object designated by callers. Here, because I'm writing the code inside the implementation, I do have access to head.next, and I don't need to use the method get. Let's save this. Let's compile the test. javac test.java, java test. Okay, so you see, we could have done a better job here. Let's fix this. System out, print line, outside, system out, print line, inside, so that it's pretty. Let's skip a line like this. Compile our test. Run. Okay, so outside and inside are doing exactly the same work. We're printing all the elements. And now what we are interested in is to talk about the efficiency of these methods. Okay, so I want you to think I want you to possibly pause the video, and I want you to think about which implementation is the fastest one. Okay, so I'm currently looking at a slide for our discussion. So I have an implementation where I was accessing the elements, but I'm outside of the implementation, and I have an implementation where I'm inside. And what we want to know is there one that is faster than the other? Is one significantly faster than the other? And if so, what's the reason behind this? We want to truly understand what's the reason behind this. Here, this is the runtime for some tests that I did. So here, the execution time is in nanoseconds. What I'm calling A is inside. What I'm calling B, it's outside. This is the one that was written in the class test. This is the implementation that was written in the class linked list itself. Okay? So you should appreciate that the difference is actually quite significant. And we want to understand why this is the case. Okay? If I move forward a little bit, you're going to see that when we reach 1,280,000 nodes, the implementation inside the list takes 5.92 milliseconds, whereas the approach where we are outside takes 45 minutes. Okay, so here this is in test versus linked list. As I said, pause the video if you need. Make sure that you have a good go at finding by yourself the reason for this absolutely huge difference. Here, think about this. We're implementing some game. The list contains several polygons that are rendering the scene, and in one case we are able to do this operation in 5.92 milliseconds, so it should be almost instantaneous. In the other case, 45 minutes. We would not sell any copy of that game. That's a failure. So what I'm interested in is actually a mathematical relationship. I want you to tell me the time that it takes for this implementation varies in the following way. Let me show you how I created my example here. Every time I am multiplying by 2 the size of this list. And as you can see, for the implementation inside, the time is more or less doubling as well. Which is optimal. Every time I'm making the list twice as big, the time that it takes to traverse the list is twice as long. However, if you look at implementation B, you will see that the time is actually multiplied by 4 each time. Do you see why? Can you think of an explanation for this? For sure, the Implementation outside is required to make calls to the method get. Let's forget about its implementation for a second. If it was only the overhead created by making a method call, I would expect that this overhead would be very small. Actually, the solution that I will provide you in a few minutes will actually make several method calls from outside, but it will be as fast as the one inside, almost as fast. Let me show you the following. Okay, so you will remember that the method get has the following implementation. Every time there is a call to get, P is positioned to head. And here in the slides, I'm reminding you that I'm using a singly linked implementation and it has no dummy node. So here, I'm going to go inside this for loop a number of times, which is proportional to the argument. So if there's a call to get of 0, I don't go into the loop. P was already pointing at head. I'm returning P dot value. If the call was for get of 1, P equals head. We go inside the loop one time. P equals P dot next. We return P dot value. We visited 2 nodes. If this is a call for get of 2, we position P on head. We will go twice inside the loop and we return P dot value. We visited 3 nodes. But here, this get is called for every iteration of our for loop inside the method traverse inside the class test. If we actually replace get by its implementation, it means that the work that we're doing is equivalent to this. For I equals 0 to size, position P to head. Go inside the loop a number of iteration proportional to where we are right now, I, and move. Each time printing the value. This means that a call to get of 0 requires visiting 1 node of the list. A call to get of 1 requires visiting 2 nodes of the list. A call to get of 2 requires visiting 3 nodes of the list. A call to get of 3 requires visiting 4 nodes. In the general case, a call to get of n-1 requires visiting n nodes. But we have made all these calls. So the total number of nodes visited is the sum of all these numbers. So therefore, it's n times n plus 1 over 2 nodes were visited. This is proportional to n squared, and it explains the behavior. Every time we multiply by 2 the value of n, the time that it takes is multiplied by 4. Okay, so that explains very well the observed behavior. So we need a way out. We need a way to solve this problem. We want to be able to traverse the list from outside, and we want to do it fast. So the problem that we will be solving is as following. We want to create a method or a mechanism to traverse the list, meaning visiting each and every element one by one in order when we are outside of this list. Of course, the user does not have access to the nodes. We will not make any compromise on encapsulation. And it has to be clear what the mechanism that we will be providing is very specific. It's a mechanism that will allow us to visit all the nodes sequentially. This is by no means a general solution for speeding up get. It really is a way to traverse the list. So what is it? This concept will be called an iterator, and it's uniform and general. Uniform, so it's the same mechanism will be applied for all the data structures that are present in the collection of Java. So this is true for the list, but also the trees and all these other data structure that you will see inside the in the data structure course. Okay, but it's a mechanism that visits the element one at a time. Very important. Okay, so what's an iterator? An iterator is an object that has a method next and as next. Now the important question is, who will be responsible for implementing the iterator? That's the first question that we need to answer. Let me show you what I mean, what I'm expecting, what the behavior should be for this iterator. If I have a list and it contains these 5 elements, 0, 1, 2, 3, 4. What we want is that conceptually, the iterator is before the first element. We're at the start of an iteration. We have not started an iteration yet. And now there will be a call to the method next. The iterator has moved over the first element and it has returned the value of the first element. That's conceptually what we're expecting. Before the iterator is at the start of the list, we call next. It returns 1 and it has moved past. It returns 0, sorry. It returns 0 and it has moved over the element. If there's a new call to get to next, it returns 1 and it has moved over the first element. It's positioned in between the next 2. Call to next, it returns 2 and the iterator is positioned after. Another call to next, it returns 3. It's positioned before the last one. If we call the method hasNext, it should be returning us true because we're not done with the iteration. The iterator can still be called. We call the method next. It returns the value 4. The iterator is now positioned after the list. If we were to call the method hasNext, it will return false because it would be an error to return a value. We are done with this iteration. Okay, so that's the expected behavior. I'm going to propose you a first implementation that we will actually throw away very rapidly. But still, it's going to be a stepping stone. It will allow us to understand the concept. Here, this is the object of the class linked list. Has a variable head, and I decided to give the responsibility of implementing the interface iterator to the list itself. So I'm adding an instance variable to the linked list. So its state now allows it to keep a bookmark on the list. It's now able to remember what was the last value that was returned by a call to next. I really look at the iterator as some kind of bookmark. You ask the iterator, are there more elements in the iteration? Yes, there are more elements. Give me the next one. It's returning you the next element in the iteration. And then it memorizes where it's at in the iteration. So for the implementation in the slides, I have a singly linked list with only a head pointer. And my strategy is current equals null means I'm before the first element. I have not started an iteration. Calling the method next, the iterator will say, okay, I need to start this iteration. I will copy the value of head in my instance variable current. I will return current.value, so it returns A. And conceptually, the idea is that the iterator is now positioned after A, conceptually. If we ask the method has next, can I call the method next? Would there be more elements in the iteration? It will say yes here. We call the method next. Here, current is not null. I'm already in an iteration. Let's copy current.next in current. As a result of that, current is now pointing at the next element. We return current.value. This is B. The iterator is now positioned conceptually after the first element. Now, if we ask the method has next, are there more elements inside this iteration? It's going to say yes. We call the method next again. It copies current.next into current. As a result of that, current points here. We return current.value. Conceptually, the iterator is after. If we ask the method has next, are there more elements? It's going to say no this time. It's going to return false. That's because current.next is null. And you clearly see that it would cause an error to call the method next again, because what we would do is current equals current.next. As a result of that, current would be null. If we were to return current.value, we would get a null pointer exception. Okay, so that's what I'm proposing as a solution. It's not going to be our final solution, but it's going to work and it's going to be fast. There will be some flaws, but still it's going to work and it's going to be fast. Now, in the implementation that we will be writing the code, the list is doubly linked and circular. If we focus our attention at the bottom, my implementation of the iterator will be very similar, but with some small differences. So I will still use a variable called current, but because we have a dummy node, I will initialize current to be pointing at the dummy node itself. And here we will think about it as I'm before the first element. If we call next, it's going to copy current equals current.next. So it's going to move the iterator here. We will return current dot value, so this B, and the iterator is now conceptually in between these two elements there. Are there more elements in the iteration? Of course. Let's say current equals current dot next. The iterator moves here. We return current dot value. If we ask the method has next, are there more elements in the iteration? Of course. So therefore we can call next. It will copy current dot next in current and return current dot value. If we ask the method has next, are there more elements in the iteration? Here we want it to say no, to return false, because we are at the end. We are at the end because current.next is pointing at the same place as head. It's pointing at the dummy node. And this implementation of our iterator inside the circular list with a dummy node is actually easier to make than the other one. So here, and it will work all the time, in particular, when we have the empty list, current will be pointing at the dummy node. And here, if we ask the iterator, are there more elements inside the iteration? It's going to say no, because next is pointing at the dummy node, the variable next. Okay, let's code this thing. So we actually need the interface iterator. Let's copy from O3 iterator.java here. Let me show you what iterator looks like. Public interface iterator has a method next, returns something of type E, and has next a boolean. We said that for now we're going to give the responsibility of implementing the iterator to the list itself. So here, this is a good example that a class may implement multiple iterators. Here it says a linked list can be seen as a list having methods size, get, etc. Or it can be seen as an iterator. It has next and has next. Okay? That's our first implementation. Our final implementation will be different. We said that the list will have one additional instance variable called current of type node. That's the iterator here. Current is initially equals to null. We are before the first node. We're at the start of the iteration. Right now, if I were to compile the list, it should tell me, no, you're not fulfilling our contract. You told me that you can be seen as an iterator, and yet you're not providing an implementation for next and has next. Okay? Linked list is not abstract and does not override the method has next. Okay, to have the list compiled, we need to make sure that we have an instance method has next, as well as a instance method private e next, like this. I always like to be able to compile an implementation as soon as possible. So I'm going to write throw new unsupported operation exception not implemented yet. I'm going to do the same thing here. Save, compile, error. Next, private. Oh, I made it private. Cannot make the method less visible than what the interface says. So now it compiles. Why was it important to me that it compiles? Because I want to have the compiler on my side helping me detecting errors as soon as possible. That's why I started my implementation like this. So now I know that everything that I've added to the list so far, at least from the point of view of the syntax and the types, is sound. So what has next? We are in the implementation where we have a dummy node. The implementation is quite simple, actually. If current.next is different than head, we can move forward. Okay? Remember, if the list was empty, then current.next would be pointing at head, and here we would say no, you cannot call the method next. There are no elements inside this list, so you cannot iterate. However, if there were elements, initially current is pointing at the dummy node, current.next is not null, it's valid to move forward. What's next? Well, we've said it. So first we have to see if has next is false, if there are no next element, throw new no such element exception. Okay, should not call the method next if there are no, if we're at the end of the iteration, if there are no elements in the list. Otherwise, move forward. Current equals current.next. Return current.value. Okay. Let's see if we can use this mechanism. With an iterator. We want this to be pretty. We're gonna have a new line here. Here, iterator for string I. Java-C test.java. So far, so good. What can we store inside I? The reference of an object that implements the interface iterator. Color does implement the interface. That works. While I has next, let's print I.next. Okay, so I has a method as next and next. That should be okay. Java C. And now let's run our test. Whoops. Null pointer exception on line 45. Okay, so we've done something wrong. Oh yes. Oh yes. I made this mistake. Obviously it was not intended, but it's a good example. In the implementation where we have a dummy node, the idea was that current would be pointing at the dummy node. Okay, good. Let's recompile our linked list. Let's recompile, well, no, the test doesn't need. With the iterator, bleu, blanc, rouge, jaune, vert, orange, this seems to be working. Okay, so not too complicated. What we said is, let's give the responsibility of implementing an iterator to the list itself. In order to do this, the object of the class linked list has an instance variable current. Initially, when the list is created, we would set current to be pointing at the dummy node. The method has next would return true if current.next is different than head. We're not at the end of the list. Current.next is different than the dummy node. The method next. If there's no next element, throw an exception. Otherwise, move forward, return a value. Okay, so I like this idea a lot. It's giving you a good intuition for what's the state of an object. Okay, so here on the implementation that we have inside the slides, the one where we are using singly linked nodes, initially current is null, and this means we're before the iteration. When we start the iteration, we say current equals to head. After that, for every call to next, we say current equals current.next. And what I mean by state is the fact that the list now memorizes the last position that was visited by this iterator. It's only a call to the method next that will move the iterator forward. Okay, so question is now, is it fast? Here's the result. Traversing a list, when we are inside, when we have 1,280,000 nodes, 5.92 milliseconds. When we use the iterator that we just created, 7.2 milliseconds, barely 13% slower than the implementation where we are inside the implementation. So this is a very very good results. No compromise is made in terms of the encapsulation. We've never made any variable public. All the variables are private. We're providing a mechanism to visit every elements of this list. And it's fast. It's super fast. So, what's the problem then? What's wrong? What's the biggest restriction that we have for our implementation? The biggest one is that there's only one iteration at a time. If we wanted to have 2, 3, 4, as many iterators as we want on the list, we cannot achieve this. If you want, you can pause this video and think, how would you solve the problem? With the knowledge that you have, how would you solve it? I can tell you, we can solve this problem with the information that you have, with the knowledge that we have so far in ITI1121. We can solve this. Okay, if you made a pause and you're back, I'm going to show you some memory diagrams of my solution, and I want you to reverse engineer my solution. If we want to have multiple iterators, it means that there will be multiple instances or multiple variables of type node, each one of them pointing at a node. They could be pointing at the same node, obviously, but pointing at a node of the list, and they're like a bookmark on the list. They're pointing at a node and they memorize where we are in the iteration. And the idea will be like before. So here you can imagine that I can have I is pointing at this iterator, J is pointing at this iterator, and I want, if I call I.next, what I want is that we will copy current.value into this particular variable current and return current.value. So that's going to be the behavior of our iterator. Okay, so now we have a challenge. How do we do this? Okay, so we cannot give to the users of the linked list the possibility of declaring themselves variables of type node. We can't, because the nodes are private. We want to keep this implementation private. The instance variable next is private. So we cannot allow programmers outside of the class to have a direct access. As the diagram is suggesting here, these instance variables are inside some objects. And it's these objects that are the iterators. So here I have two iterators. An iterator is an object, and its class implements the interface iterator. What it means is that this object has a method next and a method has next. So for this next implementation, what we're going to do is we will be declaring a new static nested class that we will call myListIterator. And it's that particular class that will be implementing the interface of it, the interface iterator. We're now giving the responsibility of implementing the interface iterator to another class. Okay, let's work on this. So we're going to use another static nested class. Let's call it myIterator. It has its own type. If we want to avoid confusion, let's say that the type is U, implements iterator for these things of type U. So it's no longer the case that the list is responsible for implementing the iterator. It's objects of the class myIterator that will be doing the job. The list no longer needs an instance variable current. I have now to change this. The method hasNext and next are implemented by the iterator. As before, I really like to have a strong starting point where I know that everything is safe in terms of syntax and types. So throw new unsupported operation exception not implemented yet. Okay, so normally in class I would ask you if this would compile or not, and with your help we would make sure that we don't have any compile error. Okay, let's now javac linked list.java. Okay, so made a typo, obviously, because I decided that the type here would be U. Whoops. Okay. It compiles. Okay, so what this means is simply that there are no syntax error, and from the point of view of the types, so far so good, this seems to work. What are the instance variables? So private node, and here U is our type, current. Here, what we said is initially when the iterator is created, current will be pointing at the dummy node. If the instance variable is pointing at the head node, the dummy node, then this means that we're at the end. So there's an X if it's not pointing at head. Here, if hasNext is not true, so not hasNext, throw new, no such element exception. Like this. Otherwise, move forward. Current equals current dot next and return current dot value. Now we said that the work of making current pointing at the dummy node would be done when we create a new iterator. So let's implement a constructor. Private my iterator like this. And here we want to say current equals some head. And here, look at this. Will this work? Will this compile? The reason why I'm making this very long pause is because I know that it will not be compiling. I know that there is an error. If you want, pause this video and think. Where will this error be reported? What is the problem? Let's compile. Okay. There was a syntax error that was not expected. Where is it? Return here with 2n. That was silly. Let's compile again. So here, do you see what's wrong? We're trying to access some variable head from a static context, and head is a non-static variable. That's not going to work. So the iterator has to know to which list it belongs. So what I'm going to do, I'm going to propose to tell the iterator what list it belongs to. So here, that would be linked list of type U, my list, and we would make the iterator remember what list it belongs to. This my list equals list equals my list. Here it's going to be my list dot head. Here as next it's going to be my list dot head. And now it compiles. Okay, so an object of the class myIterator is told you belong to this list or that list. It's when constructing an object of the class myIterator that we would provide the list that the iterator belongs to. And then knowing that, the iterator will now have access to the variable head of the list that it belongs to. Can actually show you some memory diagram for that. Okay, so So here, this is an object of the class myIterator. It has an instance variable current, and it has an instance variable myList. This is another object of the class myIterator. Its instance variable current is null. In the singly linked implementation, this means I'm before the start of the iteration. It has an instance variable of type myList. This is myList. And if we are to call i.next, it's going to say, my instance variable current is null. I am before the start of the iteration. Let's start. Let's copy myList.head inside current, return current.value. So we're starting this iteration. If we call j.next, the variable current of the object designated by j is not null, so therefore it's already inside an iteration. It's going to say current equals current.next. It will move forward and return d. Here, on our implementation, let me remove all these annotations. Okay. So an iterator is an object that has a variable called myList and a variable called current. So the iterator is for this list and this one as well. Somewhere in some program, we possibly have I see that you cannot see. Okay, so I'm gonna try to make this, fortunately, having a hard time making this smaller. Okay, if I do this, you can barely see. Okay, so let's start over. Okay, let's go here where you can see my drawings. Okay, so we have myList and current. MyList is at the top, current is at the bottom. Okay, let me just do a little thing here. Okay, so at the top is myList, myList at the bottom, current. Let's have I pointing here, J pointing there. They're both iterators for this list. And I is pointing at the dummy node, and in J, current is pointing here. If we call i.hasNext, it will say yes, there are more elements inside this iteration because current.next is not pointing at the dummy node. Current.next is different than head. If we call i.next, it will copy current.next to current. As a result of that, current will now be pointing at the last element of the list. For both iterators, if we ask I dot has next or j dot has next, they will both return false because current dot next is equals to head. Okay, back to our implementation here. I can show you here artificially how I would be creating these objects. Okay. So here, let's have a linked list for some string A and B. Let's say A equals to new linked list for some string like this. Let's have B here. Say B dot add last alpha bravo so far so good. This compiles. Can declare an iterator for string I and j. I equals to new iterator for string, and I'm going to pass A and iterator j belongs to B. Oh, I was not paying attention. We called it my iterator, and the compiler, very friendly, reminded us of this. Okay, so now I could say while I dot has next system out print line I dot next. We expect that this is an empty list. I've added nothing inside A. And while J has next, let's print J dot next. Now linked list as a main method, I'm executing it, it works. But now that doesn't seem so useful. I'm inside the implementation of the class linked list. How will someone from outside of this implementation actually be able to create these objects? I'm looking for my class here. How would someone from outside be able to create these objects of the class myIterator? And the answer will be, let's provide a method, public method. It's an instance method, iterator E. So here, objects of the class linked list are using the generic type E. Just lost the method that I want to create. Where is it? Oh, it's right here. Okay. So, public iterator for some E. And if I follow the nomenclature of Java, they're calling such a method iterator. And this method will simply say return a new myIterator for some E on this list. That's the magic here. So here iterator is an instance method of the class linked list. It's creating the iterator and it's for this particular list. Let's see if this compiles. Compiles. Let's see how we would use this from outside. So here, I is an iterator. But it's no longer true that linked list implements the iterator. Rather, linked list provides a method called iterator that returns on it an iterator on this list. See, it works. We've created an iterator. So what's an iterator? So it's no longer true that the list implements the iterator. The list implements the interface list only. We now created a new static nested class called myIterator, and it's this one that's implementing the iterator. But because it's a static nested class, it needs to be told to which list it belongs. What is the list that this iterator will be iterating? When it's created, where does it find the header of the list? Where does it find the variable head? It's by using its variable my list here. Okay, so that could be the end of the story. That could be it. That could be our iterator. It could be just that. It would be perfect. Now we've solved the problem. What I mean by that, we now have an iterator, a mechanism that we can create as many iterators as we want for a list. 1, 2, 3, 4, 5, 10 iterators. That works. We just need to call the method iterator. So here, if I wanted 2 iterators, so I and j, I just need 2 calls, I and j, and we could traverse the list twice here, or even we could intertwine these two lists, these two while loop if we wanted to. We could do what we want. Let's see if this works. Java C test, Java test. you see with the iterator, we printed the list twice because we had two iterators. Okay, so we have a static nested class myIterator. Each iterator memorizes a position inside the list. And it's as simple as that. I'm not done with the iteration if current.next is different than the dummy node. And next simply moves forward and returns current.value. Okay, so as I said, that could be enough. We would have solved the problem. It's very fast. Multiple iterators. It works. But we could do something more elegant. The problem that we faced here, where the iterator needed to be associated with one list, one object of the outer class, is a very frequent problem. In Java, in particular, when we are implementing linked structures, when we are implementing GUI, graphical user interfaces, we're facing this problem often. So therefore, we're going to look at a new Java concept that solves this problem in an even better way. I don't know if you had a chance to see this, but on the internet, there's a website called Java Ranch. And it has very funny stories. And one of them is called Getting in Touch with Your Inner Class. And you have the URL there. And it goes like this. Attractive object seeks that special someone for sharing private thoughts, walks on the beach, drinking wine from a glass, subclasses and pets are okay, no static. And then it goes to show that an object of an inner class will be automatically connected to an object of the outer class. And there can be as many objects of these inner classes as we want. What's an inner class? Simply this. We remove the keyword static. Now this iterator has access to the type parameter of the class. This connection that we were making ourselves is now automatic. Now the object, because it's created from a non-static nested class, this object will be automatically connected to the outer object that created it. Why we do this? Because the iterator now has access to the instance variable head of its outer object. An object of an inner class is connected to its outer object and has access to the instance variable of the outer object. Okay, I'm going to remove my main method because it's no longer compatible with what we just did. Okay, so let's review what we have. It's still the list. The linked list is a list. An iterator, will implement the interface iterator. Good idea that we review the code. So it's an object of the class myIterator that implements the interface iterator. This object no longer needs a type value because it already gets the type from its outer object. And now we also need to change this when we create the object myIterator. Okay, so we actually no longer, yes, we need a constructor like this, but we no longer to tell this myIterator who's the other object. It knows it. Okay, so we have made many changes now. Okay, was a bit careless here. Current is pointing at nodes to store values of type E, just like my outer object. When I'm returning something, it's of type E. Does it work? Yes, it does. Okay, so a fairly simple but deep idea in Java. We often need to have a nested class that will be creating some implementation. We want this object to be connected to the outer object. So here, let me show you. The inner objects are objects of the class myIterator. The outer object is an object of the class linkList. It's the object of the class linkList that is creating these myIterator objects. Okay, so an inner class has access to the variables and the methods of the object of the outer class. And such an object can only be created in the context of an outer object. Okay, just moving forward, showing you here. So before we had to create this connection between the iterator and its list ourselves. If we drop the keyword static, then the myIterator object needs to be created from an instance method of the outer object, and Java will take care of making this connection between the iterator and its outer object, its linkList. It will be done for us. We say that the namespace is shared, meaning that when a method has next of a myIterator is talking about head, head is not a variable of the object myIterator. Head is a variable of its outer object. Okay, so this is our final implementation. It's a inner class. The iterator is an object of an inner class. This allows us to create as many iterators as we want for a list. Each one of them, because they're from a non-static nested class, has access to the variables of the other object. That's what we wanted. This allows us to have multiple lists and multiple iterators. So here, I is associated with the list designated by L1 because I was created like this. L1 dot iterator. So it's a call to the method iterator of the object designated by L1. It's a method in the context of this object that created the iterator. Therefore, it's associated with L1. Here, K was created by a call L2 dot iterator. Iterator is an instance method of the class linked list. It was called on the instance designated by L2. It's this object. So therefore, the iterator is connected here. When we say k dot next, here k looks at its instance variable current. It says, I'm inside a singly linked list with no dummy node. Current is null. I'm before the iteration. I need to start. Let's copy head into the instance variable current. So it's this head that's copied here. On the other hand, when we call I.next, because the iterator designated by I is associated with this object, when we execute current equals head, it copies this variable head to current, so it will start the iteration here. Okay, and if I call j.next, well, current is not null, current.next is not null, we can move forward, copy current dot next to current, it moves here and it returns current dot value. Okay, so here, is it true that j dot has next true? Yes. Copy head into current. Is it true that I.next is valid? Not is returning true? Yes. We call next. It moves forward, etc. Okay, and this is very fast. I've now created 2,500,000 nodes. We see that the implementations that are inside the list and using the iterator are now very fast still, yet the implementation that is using get in that case was taking 4.1 hours. So this is really a valuable thing to have. So hopefully you will appreciate how this has allowed us to think about a lot of concepts that are related to object-oriented programming. We've been able to create a mechanism that allows us to traverse the list one element at a time. The method hasNext returns true if a call to next is possible. The method next returns the next element in the iteration. In order to create our final implementation, we've used an inner class. This is a nested non-static class. And the idea is that an inner class has access to the variables of the outer object. That's why we use an inner class. You should appreciate as well that the class node has no methods. It doesn't need to access the variables of the outer object. That's why we keep it static. It would create further problems down the road if we were to make the class node not static. Okay, so that was it for this lecture. In the next lecture, we're going to be talking about recursive list processing. So it's going to be essentially another way of traversing the list, but that time we're going to be using recursion.